Okay, thank you very much. So first I would like to thank Moriwaki Sensei and the mathematical department of Kyoto University for the kind invitation. So it's my pleasure to come to Kyoto again and to give this lecture. So as Moriwaki Sensei has said, the final purpose of this course is to introduce a joint work with him. On Arakelov geometry. Of adelic curves. So, Arakelov geometry is a branch of arithmetic geometry where we use ideas of algebraic geometry to attack problem in number theory. So the idea consists of seeing number fields like some analog of a function field of a curve, and try to use algebraic geometry ideas and methods to solve the problems of number theory. So there are several difficulties in such a comparison that I will explain progressively during the course. So I will recall briefly the program of the course. So first of all, I would like to introduce a classical geometry of numbers. So which are fundamental in Diophantine geometry. And then I will talk something about algebraic geometry. Of a curve. And you will observe some similarity between these two settings and also their difference. And then I will introduce so-called adelic curves. Grossly speaking, so it is a framework which permits to unify the treatment of number theory setting and function field setting. And also it permits to include other settings which are very natural but not belong to these two types of things. And then I will talk about some Arakelov geometry. In a general setting. So today I will mostly focus on the geometry of numbers and how to view it in some modern way of Arakelov geometry of a number field. So I begin the first lecture. So in geometry of numbers, the most fundamental objects are lattices in the Euclidean space. So I just give the definition. So we take some integer n. So by a lattice n, so we mean a subgroup of n generated by a basis of n over R. So formally, it is of the form lambda, which is A1 E1 plus etc. plus AN EN. So I note this like lambda E. So here E is a basis. So lambda E is just like this. But here A1 to AN. Just the integers. So I can drop a map in the graph in the case where n is 2. So you just find something like this. So of course, please ignore the lines. Just these points are points in the lattice. So here I take a basis like this, E1 and E2, and so the integral combination of this basis will provide the points in your lattice. So of course, you can find another basis which generates the same lattice. So for example, if you take E1 like this, and you take another vector to form another basis, and essentially you will find the same lattice. So different bases may generate the same lattice. So, however, there is an invariant. So if you take these vectors E1 to En, these are vectors in Rn, so you can put them together. So you can put E1, E2, etc. En. So you consider them as column vectors, and then you find a matrix, n by n matrix, so you can calculate the determinant. And if you take the absolute value of this determinant, so that's not, so only depend on the lattice. So if you, so I note lambda on this lattice. So this quantity is denoted by d lambda. D of lambda. So let me go back to this graph. So if you take the parallelogram generated by this basis, so if you take this parallelogram, so which is called a fundamental domain. So if so definition. So D, I let D be the set of A1, E1 plus etc. plus A and En. So with AI 0, 1 for any I. So this one is called the fundamental domain. Of lambda. So of course that depends on the choice of the basis. So with respect to E. And then you can find that d lambda is just the volume of this fundamental domain. So maybe I write dE here. So we will see that the volume of this thing will not depend on the choice of the basis which represent the same lattice. For example, if you take these two vectors and then you find another parallelogram, so even though these two parallelograms are different, they have the same volume. So you can get it rather directly. So now, in geometry of numbers, we try to understand the geometry of such lattices by using their invariants. So of course, d lambda is not the only interesting invariant, but it's the most fundamental one. So let me give you a very elementary lemma. Of Bldg field. So it's rather general. So you take simply a Borel subset. So you can count the you can count the lattice point in the Borel set. So that's NA be a map from Rn to a set of positive integers plus infinity. So the function defined as an NA of x is a cardinal of lambda intersection with a plus x. You just move your Borel set, you translate the Borel set by the point x, and then you count the number of lattice points in this translated set. And then the conclusion is that the function A is lambda periodic. And you have a low amount for superhuman of x in Rn. By the volume of A divided by d of lambda. So it means that, of course, you can try to find some Borel sets which don't touch lattice point. The lemma said that if you allow to move your Borel set arbitrarily, and then at some point you will find, at some translation you will find many lattice points if the volume is big. So I will explain the proof of this lemma. So already you have seen that the invariant d lambda appears in such a situation. So I introduce some notation for S in Rn. We just let a function indicate a function. So indicating if a point belongs to S or not. And then if you use this notation, you can write NA of x as follows. It's the sum of u in lambda, indicator of a plus u minus x. And if you write in this way, you will find immediately that and is lambda periodic. So if you translate x by some lattice point, then you modify a little bit this translation. So you find the same expression. And so it permits you to pass the function to the quotient space. So you can find a unique function, tilde, so which is defined on the quotient set. So such that if you compute the class of some point U, so this is just any of x for any x. So now, so how to relate this function to the volume of the fundamental domain? So you will see that the fundamental domain, it just represents this quotient space. So if you integrate over n divided by lambda, so this function, so I introduced some change of variables to so this one you can find this as the sum, because here A is given by a sum. So you can integrate over some fundamental domain. You will find this function and just put the expression of A here. Instead of integrating over the quotient space, I integrate over some fundamental domain. And then you will find that this is just the sum of U A lambda. So the volume of A intersection with D minus U. And the miracle is that if you put the union of D minus U, that is a union without intersection, and this sum is nothing but the volume of A, because you compute the volume intersection of the volume of A intersection with each translation of the fundamental domain, and you calculate the sum. That will produce you exactly the volume of A. So here you can make some upper bound, this by the superscription of x in R of n, and A of x. So multiply by the by d of lambda, because the volume of a fundamental domain, or the volume of the quotient space is just d lambda. And then if you put them together, then you will find this one is bounded from below by the volume of A divided by d lambda. So how to? What are the application of this this result? So, for example, you can deduce the first theorem of Minkowski from this lemma. So we will introduce some more notation. So. So here the problem is that we need to move the Borel set in order to get many lattice points. But in the case where your Borel set is convex, then you need not to move. So by convex body, in R2 power n, we mean a convex and compact subsets delta in R to power n such that the interior of delta is not empty. So if in addition for any x in delta you have a minus x also in delta, we say that delta is symmetric. So I will give you some example. So if you draw a disk in R2, so this is a symmetric convex body. So you can guess other examples. So now, given such a notation, you announce a theorem. So what is Minkowski's first theorem? So I just announced I just present the symmetric case. So for general case, you will have a very similar proof. Be a symmetric convex body. And then you can compute the number of lattice points in the convex body. So this one is bounded from below by 1 over 2 power n, volume of the convex body divided by d of lambda. So you have some coefficient here, because you are not expected to move your convex body. So I will explain the proof. So where comes this coefficient 1 over 2 power n? That is because we need to pick a smaller Borel set. So apply lemma to A, which is 1/2 of this symmetric convex body. And then we obtain that A, which is Ax, which is the existence of some x in Rn, such that A, which is a cardinal of lambda intersection with A plus x, bounded from below by a volume of A, divided by d lambda, which is 1 over 2 power n, because A is 1/2 of delta, So we are in n-dimensional space. So we will find 1 over 2 power n volume of delta over d of lambda. And then now, so what can we do with this? So if E is in a lambda intersection of A plus X, and E prime is also in this set, and then you can compute E minus E prime. So I explained that this will belong to delta and also belong to lambda. So this belongs to delta because A is 1/2 of delta, and the delta is a convex body which is symmetric. So so 2 of E so belongs to 2 of E minus X belongs to delta, and the 2 of E prime minus X belongs to delta also, and if you put a minus here, belongs to delta also, and then you take the average of these two vectors that will produce E minus E prime belongs to delta. And as these are lattice points, their difference is also a lattice point. So you get this one. And so you can fix a point inside as a reference, and then you compute the difference of other points with this reference point. That will produce you different points inside delta intersection with lambda. So there are at least such points inside this set. So let me give you the proof. So the cardinal of lambda intersection of delta is at least this one. So you have found that d of lambda is very fundamental invariant, which gives you some geometric information. So that is one of the examples. So then I will introduce more invariants and make some link with analysis. So before introducing other invariants, I would like to talk about some Fourier analysis of lattices. So the idea is based on the fact that in a Fourier transform, if you take a density function of a normal distribution, then it is a function which is in some sense invariant under the Fourier transform. So the basic idea is like that. So these invariants will produce you some very precise estimations that I would like to explain in the remaining of the talk in the morning. So if A is some subset of R to power n, we just let rho of A, which is a sum for any x in A, exponential minus pi the norm of x squared. So you see that this one is just the evaluation of the Gaussian, so a normal distribution function on the point x, and you take the sum. So this norm is the usual Euclidean norm on R to power n. So namely the norm of x1, xn is just square. It's just the x1 square plus x2 plus xn square. So now I fix also lattice, so I will not introduce again the notation for lattice. So the proposition says that for any x in R to power n, you will have a row of lambda plus x. So as before, lambda plus x is a set of u plus x for u in lambda. So if you compute such function rho on this set, you compute the sum of exponential Gaussian distribution function evaluated on this set. So this one is always a finite sum. So this, so how to say, you consider this as some series. The series will converge. So moreover, so this is a very good function. So rho lambda, which is Rn to R, is lambda periodic. And the so smooth of class C infinity. So this is of course here I'm not counting the points. So this function is not the same thing as counting of number of points in A, but it's not that far away from counting function, because exponential minus the norm as viewed as a function will decrease very fast to the infinity. So near the origin point, it's almost 1. And far away from the origin, it will decrease very fast. So it permits to detect the number of points around the origin. So that is the motivation of introducing such functions. So it permits to distinguish points which are very near the origin and the points which are very far away from the origin. So okay, so I will explain a little bit why. So it's a very common exercise in analysis to prove this statement. I will just mention a little bit how it will work. So here you need to make a sum. So you can write this function, so rho of lambda plus x as a sum of a point in lambda, exponential minus pi norm of u plus x square. So the point is that if you take a basis of lambda, so if EI is the basis of lambda, and x is of the form b1 e1 plus h2 plus bn en. And then you can rewrite this sum as the sum of a1 an in z2 power n, exponential minus pi, the norm of a1 plus b1 e1 plus h2 plus an plus bn en 2 power square. Somehow it is a little bit complicated to compute this norm square. So because you don't know if E1 and En are orthogonal or not. So if you know they are orthogonal, then it is very easy to compute. but you have some comparison theorem of norms on Euclidean or some finite dimensional vector spaces. So you can find some constant C, which is positive, such that the norm of lambda 1 E1 plus H plus lambda n En square is bounded from below by C times lambda 1 square, lambda n square. I just change the norm in forcing E1 to En to be orthogonal. That will give you some orthonormal, and there will be another norm. And you have a comparison of norms. So if you have two norms on the same finite dimensional vector space, they are somehow equivalent. So you can find a constant which controls their difference. So you can find a lower bound like this, and then that will permit to decompose the sum. So you can decompose it as a product, and then you take AL in Z, and E minus C pi AL plus BL square. And then I will let you do it by yourself. That's very formal exercise to prove that this will converge, and we'll define some smooth function with respect to the coefficients P1 to Pn. Okay. And now, if you have some periodic function, and if you follow some courses in analysis, especially maybe multidimensional analysis, it is very natural to construct the Fourier series of function. So before this, I will just give you a lemma showing that the Gaussian distribution function is invariant under Fourier transform. So for any theta in R, if you integrate over R, E minus pi t square. So this is a normal distribution function, and the minus 2 pi I theta t. So that I am calculating the Fourier transform of this Gaussian distribution function dt, and then you find exactly the same thing. You replace t by theta, and you find the same function. So that is fundamental to our work of this lecture. So you can, for example, introduce some coefficients here, so to produce a square. So it suffices to show that the integral of over R e minus pi t plus I theta square. So I just put some I theta square here. So dt is 1. So I'm doing nothing but putting this term on the left-hand side and to produce some square. So just give you some hint is that this one, if you take theta is 0, so you find the integral of e minus pi t square dt. So this one, the integral of this one is 1, so it's just saying that this is a probability distribution, probability density function. The integral is 1. So I will not give the proof of this one because it's another exercise for analysis course. Just how to pass this equality to this equality, I will give you a hint. So you have some very nice function which is holomorph analytic. So you try to integrate from minus r to r. and that will give you more or less this integral. And this integral require you to integrate not from minus r to r, but from minus r minus I theta to r minus I theta. So you need to r plus I theta, sorry. So you need to integrate from this point to this point. And then, so if the function is holomorph, so it's very natural to compare this integral, to compare these two integrals by the integral here and there. The point is that here you have a very negative or very positive, so how to say, real part in this power. And then you have a square with minus pi, or the exponential, which means that the value should be very small. So if you are very far away from the origin, so that's what I had to say. So if you are far away from the origin, that will decrease very fast to 0. And the contribution of the integral along this side and this side will goes to 0 when r tends to the infinity. And then it tells you that the integral like this and the integral like this are the same. So if the integral of this one is 1, that also. So I let you complete the details. Especially this one is a very good exercise for. But usually, if you look at into the literature, Gaussian density function is not exactly the same thing like that, but somehow like 1 over minus square 2 pi e minus t square over 2. But you will see that it's simply a change of a variable that will give you the equality. So the advantage of the change of variable is that you see that the Fourier transform really preserve the function. So if you apply to this function, you need to do some arrangements. And then I will propose a higher dimensional version of this formula. So for any y in r to power n, so you will have the integral over n e minus pi x squared minus 2 pi I, the inner product of x and y, and you integrate with respect to the Bldg measure, and then you find e minus pi, the norm of y squared. So of course you can try to prove it directly, but I will explain more direct way. So not more direct, but something which use this lemma. So if y is 0, then you are happy because this term will vanish. You have exponential minus pi norm of x squared. So as I said, then you are in the situation of the product of several copies. So you have integration of e minus pi x1 squared plus xn squared, and then you have dx1 dxn. So you have several copy which is somehow independent. So you can compute it as some multiple of integrals. So that will produce 1. So if y is 0, you are very happy. But if y is not 0, what you can do? So if y is not 0, so you choose some orthogonal basis. Rn containing 1 over the norm of y times y. So you can always do this by Gram-Schmidt. So you can suppose that y is just given by sum of the coordinates. And then you are still in the situation of independence. The integral of e minus pi norm of x square minus 2 pi I xy dx. So you just find the integral of e minus pi t square dt to the power n minus 1, because other coordinate does not get involved y, because y is orthogonal to other coordinates. But in the situation of the point y over the norm of y, you will find e minus pi t square minus 2 pi I t, and then you have a norm of y here, dt. And then you find that this term is 1, and this term is nothing but e minus pi, the number of y square. So you will see that in higher dimensional case, you also have this invariant property of a Fourier transform. So now I can apply a usual Fourier analysis techniques. So in one-dimensional case, usually you compute some Fourier transform and you evaluate on integral points, and then you can apply Poisson formula. And here, in higher dimensional case, somehow it's not so good to work directly like that. So because if you fix some lattice inside R to power n, so you need to pass to a dual lattice in order to get the right result. So so we call dual lattice of lambda, the lattice lambda star generated by a dual basis of lambda, by the dual basis of a basis of lambda. So you can try to prove as an exercise that the dual lattice will not depend on the choice of a basis of lambda. So of course the dual bases are not the same, but the lattice generated will be the same. So how to apply the Fourier analysis? So I'll give you a proposition. So now you have some low lambda plus x, which is a periodic function. So so you can compute its Fourier series. So it's 1 over d of lambda sum for alpha in lambda star e 2 pi I alpha x integral of fundamental domain rho of lambda plus y e 2 pi I minus 2 pi I alpha with y dy. So if I write like this, you may say that it's a complicated formula, but I will then explain why it's not so complicated. So it's just the ensemble very higher dimensional case of a very classical Fourier series. So we introduce some L2 space over D. So it's just a square integrable complex functions over D. And you have some inner product defined on this space, which is given by inner product of f and g is 1 over d lambda and the integral over d. So fx times the conjugate of gx dx. So it's a very standard way to do the Fourier analysis. And then you have an orthonormal basis. You have E of 2 pi I alpha point. So this is a function on D. You parameterize this family by lambda star. So this is an orthonormal basis of this L2 space. And now this one is just the inner product of the function rho lambda plus and this E 2 pi I alpha star. So this is just the inner product of this one and this one. And now you have you have a family you have an orthonormal basis of a Hilbert space, and you have a function to recover this function in L2 space. You just write it as the coefficient as the inner product with vectors in your orthonormal basis, and that will produce you the function. So it's not so difficult. So just a little remark. Here you have a very good function, so it's smooth, and it's not so. So it's a smooth over compact set, so it's very nice as a function. And therefore, you have not only the convergence in L2, you have also pointwise convergence of this function to it, because it's C1. C1, I think C1 is enough. And so you have a pointwise convergence, not only L2 convergence. And you have you also this convergence is uniform because lambda star is also lattice. So so you can try to write it formally if you have time. So I will give you some consequences of this summation formula. So, the first consequence is that for any x in R to power n, you will have a rho of lambda plus x is 1 over d lambda, sum of alpha in lambda star, e 2 pi I inner product of alpha x minus pi norm of alpha square. And this one is bounded from above by rho of lambda. So how to deduce this from such a formula? So I just compute the integration here. So the integration over d rho of lambda plus y e minus 2 pi I alpha y dy. So this is just the integration over d, and then you take the sum of u in lambda e minus pi norm of y plus u square minus 2 pi I alpha y dy. And then, so if you compute the integration over some fundamental domain, then a sum over lattice points, that will give you integration over r to power n, because you are integrating on each piece of translation of the fundamental domain. So then you will find the integration over r to power n e minus pi norm of x square minus 2 pi I alpha of x. So I should have put x minus u or something like that, so some translation or something like that. But so here I should put y plus u in order to recover this integration. But if I replace y by u, then the inner product of alpha and u will give you an integer. So exponential of 2 pi I times the integer will give you 1. So there is no problem to make such change of variable. And then by the formula above, you find that this is just exponential minus pi the number of alpha square. So that will produce you this equation here. So then you find something which is very similar to the same type of sum, only with an actual coefficient. So, but this coefficient is bounded from above by 1. So you recover. So you will find rho of lambda plus x. So this sum is bounded from above by 1 over d lambda. The sum of alpha e lambda star e minus pi norm of alpha square. So this corresponds to a situation where you take x equal to 0, which is nothing but rho of lambda. So this is very interesting, because if you translate a little bit the sum, so you translate a little bit lambda by x, and you compute this invariant, you always obtain something which is smaller than rho of lambda. So the optimal situation is just stay in the lattice points. So you should not move. If you move a little bit, you will decrease the sum. Okay. So several remarks of this proposition. Of course, this is an important feature. And also, you find that this sum is also some invariants, but with respect to the dual lattice. So, in particular, you have a rho lambda as just 1 over d lambda rho lambda star. And so also you have a rho of lambda is is bounded from below by 1. So that is very easy. You compute the exponential minus norm x, and you have 1 point at the origin, which lies in the lattice. So you have at least 1 as a result of rho lambda. And if you put them together, so you have a rho lambda star is at least 1. So you will find rho of lambda is at least 1 over d of lambda. So namely, if the d lambda is very small, so if the area of the fundamental domain is very small, then you have to count many lattice points in the rho lambda. Then you find some bigger thing. So that explains the idea that I have introduced before, that rho lambda detects the lattice points which are near the origin. So it could be seen as somehow the counting of lattice points in the unit disk, for example. So it can be compared to such invariant. And in this sense, this equality is very nice because it produces somehow the number of lattice points inside the unit disk of lattice lambda and its dual lattice. So it is not so common. So if you consider the classical counting problem. So now I will introduce some classical invariance counting lattice points. So I fix always lambda in Rn. So H0 of lambda has. So just a notation. So you just ignore why I introduce H0 with a hat. So just a notation. So I count the set of lattice points which are inside the unit ball. And small h0 heads of lambda is given by the log of the cardinal of this set. So for the moment, I will not explain the motivation of introducing such thing, but maybe next week when I talk about algebraic geometry, you will see the similarity of such a definition with classical algebraic geometry objects. So idea is that H0 heads of lambda is similar to log of rho lambda. So you should keep this in mind. Okay. Now, so, for example, we can give some lower bound of this H0 hat of lambda. So, for example, you will have H0 hat of lambda is bounded from below by minus log of d lambda minus n over 2 log of 11n over 8 pi minus log 2. So, of course, the inequality is not that optimal, so I just want to explain how we can use the invariant rule to study such thing. So you can use other methods like Minkowski's first theorem or something like that so maybe Minkowski's second theorem. So you need some more advanced tools. But just I would like to explain how we can use rho lambda to study such natural invariant. So as I said, you need to make a comparison of this one to rho lambda. So I give some lemma. So let x in r to power n and t in 0, 1. Then you will have a rho of t times lambda plus x is smaller than t 1 over t to power n rho of lambda. So if you increase the size, then the behavior is somehow like that. So I'll give you the proof. So you have t of lambda. If you compute the dual lattice, then you will find just t minus 1, the dual lattice of lambda. So you can prove rather easily. Then by the proposition that you see there, so you will have a proposition that board, you will have a rho of t times lambda plus x which is a rho of t lambda plus tx. So it's smaller than 1 over d of t lambda, rho of t minus lambda star. So d of t lambda is nothing but 1 over t to power n d of lambda. So if you delete lambda by t, you just multiply the volume by t to power n. And here you have t minus 1 lambda star. So here t is between 0 and 1. So you are deleting lambda star, but by some number more than 1. So you are making some larger lattice. So that will decrease your function, your invariant rho. So this is bounded from above by rho of lambda star. Just you are putting some coefficients to exponential minus something. So you are just reducing the sum. So you have this comparison. But you have seen that this one is just a rho of lambda. So you have 1 over t power n rho of lambda. So you see that some statements becomes very easy. But if you try to prove it directly without using Fourier analysis, somehow it could be a little bit complicated. So now, since in the computation of invariant rho, you have two types of behavior. So near the origin, so it's just like a counting function. So far away from the origin, so the general term will decrease very fast to 0. So I introduce some notation to distinguish points near origin and outside origin. So BR is just a ball of radius r. And BR open is just a ball, open ball. So lemma says that for r positive and t in 0, 1 and x in Rn, So if you compute a row of lambda plus x, but you just not consider the points near the origin, and then you will have an upper bound like e minus pi 1 minus t r square and the t to the power minus n over 2 rho of lambda. So it says that if you don't consider points near the origin, then you will have some extra coefficient which is very small. And if you are really far away, if r is at least a square root of n over 2 pi, then rho of lambda plus x outside of BR0, so it's bounded from above by e to the power n minus 2 minus pi r square n over 2 pi r square minus n over 2 rho of lambda. Okay. I will explain a little bit the proof. So it's not complicated. So it's just the saying that you have a natural upper bound if you know that your point is outside. So this is just by computation. So the sum of u in lambda, so u plus x, the norm of u plus x is at least r. So e minus pi t, norm of u plus x square, e minus pi 1 minus t, number of u plus x square. So I'm doing nothing but decompose the exponential with t and 1 minus t. But you know that this norm is at least r, so you can give an up bound of this one. So e minus pi 1 minus t, you just take r square. And here you have this sum which remains, so which is a rho square root of t lambda plus x, just by definition. And then you know that by the lemma, rho of square root of t, you can take it out. So it's bounded from above by the same thing, times t to the power minus n over 2 rho of lambda plus x. So it's just an application. And then here you need to take a special t. So I will give you the solution. So take t equal to n over 2 pi r square. So it's somehow some optimization procedure to detect the good boundary that you need to cut to distinguish points near 0 or outside. So it's not so complicated if you have. Okay, so now with this two, it's very straightforward to prove the above proposition on the counting of lattice points. Just I assume that n is at least 2. I let you to do this work for n equals to 1. So you need to do some optimization so that R be a parameter. So purely we don't know how at what boundary we need to cut, so we will do it at the end. So you have BR intersection with lambda is just the rho of lambda minus rho of lambda outside the BR. So this is bounded from below by a rho of lambda 1 minus e n over 2 minus pi r square n over 2 pi r square minus n over 2. So I'm just using this estimate. So at the same time, you know that this is always bounded from above by the cardinal of BR intersection with lambda. So you have some lower bound of the counting function by such a function. So now you have a BR here. So it's not good, you need a B1. So replacing lambda by R lambda, and then you are counting B1. So then you will produce that H0 hat of lambda is the cardinal of BR intersection of with R lambda. So it's bounded from below by a log of such thing, 1 minus e n over 2 minus pi r square n over 2 pi r square minus n over 2, and the plus log of rho r lambda. So rho of r lambda, so you have some natural lower bound, so it's bounded by log of d r lambda. So this is about this is nothing but minus log d lambda and then minus n log r. So you have some invariants which that you need. So what remains is to obtain some good lower bound of this one by choosing carefully r. So I will just give you the answer, but you can do it a little bit later. So I introduced some change of variables. T is 2 pi r square over n, and we need to choose some t such that e of 1 minus t times t to power n over 2 is 1/2. So please do it. Of course, it's not possible to give some closed formula for the value of t. So I just give you a hint, is that t is smaller than 1/11/4. If you choose t such that you have this one, then you can prove that t is at least, so at most 11/4. Then you get the result. So of course you can use the same idea to try to produce the more precise estimates. So in the remaining time, so you have seen how to use such invariant to get interesting arithmetic result. Then I need some result in the coming lectures that should be proved in this way. So that is a transference theorem of Bldg. So that is very important in the comparison of arithmetic invariance of lattices. Bldg. So I first introduce two invariants of lattices. So the first one is lambda mean of lambda. So this is a smaller lambda. So which is the infimum of u in lambda different from 0, the norm of u. So I just find the nearest lattice point to the origin. So it's given by the norm of the nearest points of lattice outside of to the origin, except the origin itself. So if you like, I can draw a picture. So assume that this is the origin. So maybe this one is the first point, which is nearest to 0. So lambda max of lambda is the infimum of R positive, such that BR intersection with lambda spans R2 power n. So that is the boundary that you can find a basis of the lattice. The basis of the vector space generated by the lattice. So for example, if you take a ball sufficiently large, and then you find this point and this point, that gives you a basis of R2 power n. So I think it's not exactly the same thing to have a ball containing a basis of lambda. So it's a little bit different. So the theorem, so this is a very serious, recent theorem, in fact, of Bldg, saying that lambda max of lambda times lambda mean of the dual lattice is bounded from above by n. So it is sharp in the level of power. So it is sharp for the exponent here. But maybe you can try to put some extra constant before n to produce something which is stronger. So anyway, you will see in the proof that so we will do some upper bound which is not so precise. But it is not. I think it's not possible to have a better exponent. So still, I assume that n is at least 2. So for the case of n equals to 1, it's somehow easy. So for any lambda positive, you will have a lambda mean of a lambda of R lambda is R times lambda mean of lambda, and also lambda max of R lambda is R times lambda max lambda. So in some sense, you can delete your lattice without changing the upper bound. So you multiply this by R, but this by R minus 1, because in taking the dual lattice, you need to time lattice by R minus 1. So we may assume that lambda max of lambda is precisely given by 2/3. So it's very strange, but you will see how it works. Plus 3/2 square root of n over 2 pi. I'm sorry, it is a little bit strange, but it will work. So assume by contradiction, that this does not hold lambda max of lambda times lambda mean of lambda star is bigger than n, then you will find that lambda mean of lambda star should be bigger than n over this one, but I think 3 over 2 square root of n over 2 pi is enough. So of course I can write n over this one, but you may show that n over this one is at least 3 over 2 square root of n over 2 pi. So that H be the vector space over R generated by B lambda max of lambda open ball intersection with lambda. So now you have a ball which is a little bit smaller than this lambda max, so you will not have a basis of R to power n. So this one is included in R to power n, but not the whole space. So that we can pick some points x in HR orthogonal with a norm of x equal to 2 over 3. So of course you can just pick anything with any norm, so no problem. But in a computation, you need to do some more complicated normalization. So I choose some, I think, easier one to do the computation. So now the idea is to compute a row of lambda intersection h plus x by 2 ways. So first of all, so you pick some vector inside, and you plus this vector by x, and you compute the exponential minus the norm. But x is orthogonal to h, so that is very exciting because you can separate sum and product. So you find e minus pi x squared, and then you find just a row of lambda intersection h, because this one is orthogonal. So I just bound this by row of lambda, so e minus pi x squared row of lambda. So this is smaller than 1/2 of row of lambda, because I have chosen the norm of x equals to 2 over 3. I hope that I didn't make some error here, but so pi is so big, so I'm not worried about it. Okay. So now another way to compute this is to compute lambda. So now I compute a lattice point, but outside h plus x. So this one is smaller than rho of lambda divided by b lambda max of lambda. So plus x. So anyway, h is generated by vectors inside, so I just threw out the vectors inside the ball. So this is bounded from above by a row of lambda plus x, but now you need to modify a little bit the radius of the ball, lambda max of lambda minus the norm of x. So you find that I need to take an extra 2 over 3 because of this. So I need to modify a little bit the radius. So this is bounded from above by e of n over 2 minus pi r squared times n over 2 pi r squared minus n over 2 times rho of lambda. So with r equals to 3 over 2 square root of n over 2 pi. So because of this, so real radius is this one. So I just applied the lemma that I have proved above. So the claim is that if it's the same technique if t is at least 9/4, then e of 1 minus t to power n over 2 is at least 1/4. So it is exactly the same technique here, but I need the same thing to be less than 1/4. So instead of 11/4, I need t bigger than over 4. So now if you apply this one, and you know that r is like this, you make a change of variable, and you find this one is less than 1/4 rho of lambda. Okay. So if you put these two things together, then you find that you have some upper bound for lambda plus x. So it's 1/2. So it's strictly smaller than 1/2 of rho of lambda. So you have another way to compute the same thing. So this is 1/d of lambda. So this is bounded from below by 1/d lambda. So 1 minus rho of lambda star. So the reason is that you compute 4 vectors in lambda star, but inside this ball there is no other lazy point than the origin, because you have nothing but the origin. Outside of this ball you may have some points, so you just take upper bound 1. You have 1/this one. So you have you take this one bounded by 1. So you have this estimates. So this one is bounded from below by 1/d lambda. 1 minus epsilon rho of lambda star. So by the proposition that I have erased. So here I should give the epsilon, so it's complicated. It's e n/2 minus pi lambda mean lambda star square n/2 pi lambda mean lambda star minus n/2. So it's just I just applied the proposition. So if you put this together, so you have another thing is that rho of lambda star is 1 plus rho of lambda star outside of this lambda mean. So this is bounded from above by this one. So inside this open ball there is no other points than the origin. So that will produce you a rho of lambda star is bounded from above by 1/1 minus epsilon. So you can combine this one. So you have a low lambda star bounded from above by such thing. So you can continue such lower bound. So it's 1 minus 2 epsilon over 1 minus epsilon. So okay. So you know that this one is bounded from above by 1/2 of rho lambda. So I forget. Yeah, so this is bounded from above by rho lambda. So then if you put all this together, and finally what you will get is 1 minus 2 epsilon over 1 minus epsilon is bounded from above by d lambda, 1/2 rho lambda d lambda. And the rho lambda d lambda is just rho lambda star, which is just bounded from above by 1/2 minus 2 epsilon, so which gives you epsilon greater than 1/4. And then you have some contradiction, because you know that lambda mean is at least this thing, and therefore epsilon like this should be smaller than 1/4. And then you have a contradiction. So that gives you the proof. So thank you very much. I'm sorry for passing time.